Okay, so you know when your phone recognizes your face or a self-driving car reads a stop sign? We aren't just tossing a bunch of pixels at a screen and crossing our fingers. We are funneling raw data through some incredibly intense, meticulously crafted mathematical structures. So today, we're going to unpack exactly how we mathematically teach a machine to see. Welcome to The Explainer. Today, we are taking a fascinating journey through deep learning vision architectures. We're going all the way from the early, rigid math of convolutions right up to the breathtaking paradigm shifts that are literally redefining artificial intelligence as we speak. Here is our cognitive roadmap for today. First up, the mechanics of convolutions. Second, the AlexNet and VGG breakthroughs. Third, we'll look at optimizing depth with ResNet and batch normalization. Fourth, the massive transformer paradigm shift. And finally, vision transformers. All right, let's jump right into part one, the mechanics of convolutions. You see, long before an AI could generate, say, photorealistic art, it had to learn how to just look at shapes and edges. At its absolute core, a convolution is a mathematical operation. You take a small matrix, we call this the kernel, and you literally slide it over an input to compute weighted sums. But the real magic here, it's something called translation equivariant parameter sharing. Sounds like a mouthful, I know, but it just means that because the exact same kernel weights are reused everywhere it slides across an image, the network learns to recognize a specific feature, like, say, a vertical edge or shadow. And it recognizes it no matter where it pops up in the frame. You don't have to relearn what an edge looks like just because it's shifted over to the top left corner. Let's dive into the actual grid math here. Imagine a 3x3 kernel sliding over a 6x6 input space. As it moves, and let's say it has a stride of 1, meaning it's shifting exactly one single pixel at a time with no extra padding tacked onto the edges, it churns out a condensed 4x4 output. The spatial dimensions of that output are strictly mathematically dictated by the kernel size, the stride, and the padding. That's the formula. Every single cell in that resulting output grid is a freshly calculated weighted sum of the 9 input cells that just overlapped. It's really just an elegant, highly structured way to compress visual information into meaningful patterns. Moving right along to section 2, the AlexNet and VGG breakthroughs. So, by the year 2012, scaling up these exact mathematical operations turned deep learning from this niche academic curiosity into an absolute technological juggernaut. AlexNet was the massive breakthrough here. It used an 8-layer network with larger, varying kernel sizes and essentially popularized the ReLU activation function, which absolutely crushed error rates. But a few years later, the VGG architecture comes along and radically simplifies the structural math. The VGG designers realized this brilliant geometric truth. If you stack two simple 3x3 convolutions, you get the exact same receptive field as a single, bulkier 5x5 kernel. But crucially, it uses way fewer parameters and throws in an extra nonlinearity. It basically proved that going deeper with simpler math was vastly superior to relying on fancy, oversized kernels. Which brings us to section 3, optimizing depth with ResNet and batch norm. Now, as researchers pushed these networks to get deeper and deeper, some pretty severe roadblocks popped up. When you stack dozens or even hundreds of layers, you slam into crippling problems like vanishing gradients and extreme training instability. The core issue is captured perfectly in the source material. If the input distribution shifts every iteration, the layer has to chase a moving target. Just think about that. Imagine trying to master a really complex skill, but the rules of the game change every 5 seconds. That is exactly what deep layers face, because the weights in the layers before them are constantly updating. Batch normalization steps in and solves this by mathematically fixing the input distribution to roughly a 0 mean and unit variance for each mini-batch. By stopping that endless chase, the whole network stabilizes and you can actually push the data all the way through safely. Okay, let's walk vertically through the step-by-step pipeline of a residual block, because this shows exactly how it works hand in hand with batch normalization to make these ultra-deep networks a reality. We start with our input data, pass it through a 3x3 convolution, immediately hit it with our batch normalization to lock in that stability, and then apply a ReLU activation. But step 5? Step 5 is the absolute stroke of genius, the addition, otherwise known as the residual connection. Instead of just passing the process data forward like normal, we actually add the original unprocessed input data right back into the output. Because of this additive skip connection, the network layer only has to learn the residual difference rather than the whole entire transformation from scratch. And just look at the profound mathematical impact of that exact skip connection on these lost surfaces. The visualization of the loss landscape for a network equipped with residual connections is this incredibly smooth, bowl-like surface. It just slopes gracefully down to an optimal minimum. It's super easy for an algorithm to navigate. But in stark contrast, the visualization without those connections is basically a chaotic, jagged nightmare. It's full of local minima, sheer cliffs, and massive spikes. Residual connections literally smooth out the complex math of machine learning. They're the reason we can train networks that are hundreds of layers deep without everything completely collapsing. All right, moving to section 4, the transformer paradigm shift. For years, that convolutional sliding window we just explored was the undisputed king of computer vision. No question. But if we briefly trace the timeline of sequence processing, like in natural language, networks historically process data sequentially, layer by layer or word by word using recurrent models. A very linear progression. But then, the paradigm shifted massively with the introduction of parallel multi-head self-attention. Suddenly, instead of reading sequentially or sliding a localized kernel window around, this new architecture allowed every single part of the data to interact with every other part simultaneously and completely in parallel. When you look inside a multi-head self-attention unit, what's really fascinating is what it borrows and what it completely throws away. It actually borrows the exact residual connections and normalization concepts we just talked about from vision networks. They are absolutely fundamental to making this block stable. But it swaps out those convolutional sliding kernels entirely. Gone. Instead, it relies on queries, keys, and values to calculate mathematical attention. The network literally learns to query the data to see which parts should pay attention to each other. This establishes global context instantly, no matter how far apart two pieces of data actually are in the input. And finally, Section 5, Vision Transformers, or VIAT. This really brings our whole journey full circle. The brilliant leap here was researchers figuring out how to take this NLP-native architecture, which was originally designed to read text, and reverse engineering it to process visual photographs. The mechanics of the vision transformer are ingeniously simple, yet crazy powerful. First, it literally chops a regular image up into a grid of 16 by 16 pixel patches. Next, it maps these patches into 1D embeddings using a learned linear transformation. To put that in simpler terms, it treats those 16 by 16 image patches exactly like words in a sentence. It then feeds these visual words straight into the transformer layers we were just looking at. By pre-training on a massive dataset of 303 million labeled images, the network uses global self-attention to understand the entire image holistically. It completely bypasses the need for traditional convolutions. Mind-blowing, right? So, this leaves us with a massive industry-defining question. Will transformers completely replace convolutions in vision? Think about it. We've journeyed all the way from the strict, localized sliding kernels of early convolutional networks, through the deep optimization tricks of ResNet, right up to the global parallel attention patches of today's vision transformers. Both approaches rely on incredibly elegant structural math, but their underlying philosophies couldn't be more different. I really hope this explainer has given you the foundational lens to truly understand how machines see our world. This architectural landscape is evolving at lightning speed, so keep your eyes open, keep analyzing the structures, and never stop learning.